I welcome all of you to the class, and in this class we are going to discuss now the utility of the momentum equation already discussed, and in this class we'll be discussing the Euler equations. We'll be discussing the Euler equations, or what are also known as the moment equations, the moment equation, the moment equation governing rotational motion, governing the rotational motion. The moment equation governing the rotational motion. This we'll be discussing. Now, what we have discussed right now in the previous class, that the angular momentum of a rigid body about any point P, very quickly I will write this as, was coming out equal to Ixx omega x, Ixx omega x plus Iyy omega y plus Iyy omega y plus, not Iyy, sorry, let me clean this entire thing. It was, write it at the top. Angular momentum hp of a rigid body about any point P is equal to, coming out equal, Ixx omega x, I sub xx omega x plus Ixy omega y plus Ixz omega z. That's Ixz omega z plus Ixz omega z about I cap plus Ixy plus Ixy omega x plus Iyy omega y plus Iyz omega z along J cap, and the last one was coming out to be equal I xz omega x. Do remember these equations because these are very important, plus Iyz omega y Izz omega z along k cap. Okay, this is the equation that we have already found. This was about a rigid body. If we recall, we had a rigid body beta, and there was a ground frame of reference J, and we were this body. This it was said that the rigid body beta was rotating with respect to the ground frame of reference with angular velocity of beta with respect to the ground frame of reference J. Now we had taken a point P here, okay, and from point P to a very small point having mass dm, we have drawn the radius vector r, and we were calculating the moment of inertia of this rigid body about point P. Okay, so this angular momentum of the rigid body is defined in the frame of reference in which the body is placed. The body frame of reference is beta. This angular momentum is defined in the beta frame of reference because we are calculating moment of inertia with respect to point P. Point P itself lies in the beta. Therefore, this moment of inertia is with respect to the frame of reference beta. Number one. Number two is, if P is not any point, but P happens to be, say, for example, the center of mass of the rigid body. If C is the center of mass of this rigid body, the nature of the equations is same, but instead of P here, we'll get, we'll use C. That is, this is the momentum of the momentum of a rigid body, angular momentum of a rigid body about point C now. Okay, this is the angular momentum of the rigid body about C, about point C, not about point P. The formulation of equations will be same. Number one. Number two is, now this Ixx will be moment of inertia about an axis passing through the centroid. This Ixy will be the product of inertia passing through the center of mass. This Xz will be the moment of inertia passing through the centroidal xz axis. Same is here. Okay, initially in the previous case, they were the axes having their origin at point P. Okay, if you recall what we had done in the previous course, we had assumed in the previous class, we had assumed that the point P is the point which is the origin of our XY system. This is our x-axis, this was our y-axis, okay, and this is our z-axis. This is what we had done in the previous case. The point P we had stated to be the origin of our coordinate system. Okay, therefore all these moments of inertia and the products of inertia that we were calculating were with respect to point P. Now right now we are assuming, let the point P to be the center of gravity. All the equations, the nature of the equations will remain same, but instead of point P, we'll get point C. Okay, that is, the angular momentum of the rigid body about the center of gravity is equal to this expression, where these moments and products of inertia are measured with respect to an coordinate system having their origin at the center of gravity of this rigid body. Okay, number one, we also know, let me call this equation one. Okay, we are trying to go to the equations of motion of the rigid body. We also know that, if you recall, we know an expression, an equation, that moments of a rigid body about any point, let's say center of gravity, the moments of a rigid body about any point C, okay, is equal to the derivative of, is equal to the derivative of the angular momentum of the rigid body about that very point. This is when we are discussing the kinetics of rigid body, force and acceleration. Okay, this is what we had defined there. In fact, we can solve it. I can give you a hint for this. If you look at the angular momentum is r cross mv. It is the cross product between the radius vector and the linear momentum. Okay, if you differentiate this, okay, when we differentiate this with respect to time, let's suppose r does not vary with time. Okay, then this will be r cross m. The differentiation of v with respect to time is acceleration. Acceleration multiplied by mass is force. R cross f is torque, or what we call as the moment. It's what we call as the moment. That's here. Okay, this is what is being what's written here. Okay, now we are familiar with this equation. We have already understood it when we are discussing the kinetics of rigid body, force and acceleration. That summation of all the moments about any point C, resultant of all the moments of a rigid body because of forces acting on it about any point C, is equal to the time derivative of the angular momentum of the rigid body about that very point. Okay, so this angular the summation of all the moments, this time derivative, the differentiation that we are doing here, okay, we are trying to understand the derivative of this. We are trying to understand the motion of this rigid body with respect to the ground frame of reference. Okay, so we have to take this derivative with respect to the ground frame of reference. But the problem is, as far as this angular momentum is concerned, this angular momentum is defined with respect to the point C, and point C does not lie in the ground frame of reference. It lies in the beta frame of reference. Okay, so our HC is a vector. H is a vector which is defined in beta frame of reference, but we have to take its derivative with respect to some other frame of reference, and we know the formula for that. We know, we have done it. The derivative of a vector, if you recall from the kinematics of rigid bodies in 3 dimensions, the derivative of a vector in some frame of reference, in ground frame of reference, is equal to the derivative of this vector with respect to the another frame of reference, that is beta frame of reference, plus the cross product between the angular velocity of beta with respect to the ground frame of reference, angular velocity of beta with respect to the ground frame of reference, and its cross product with the vector A. This is the derivative property of the angular velocity. When we are talking about the derivative property of the angular velocity, at that time we discussed this expression. Okay, now the problem is very easy for us. We are trying to differentiate a vector which is defined in beta with respect to the vector, which is with respect to a system which is in which it's not defined. So we can simply write this as, therefore, using this property of derivative, we can simply write this as, this can be written as, we are taking the derivative of hc with respect to the ground frame of reference, that will be equal to the derivative of this vector, that will be equal derivative of this vector with respect to the beta frame of reference, plus angular velocity of beta with respect to the ground frame of reference, that is angular velocity of beta with respect to the ground frame of reference, and its cross product with the vector itself, that is cross product with hc vector. Okay, this is the derivative of it. This will give us the summation of all the moments acting on this rigid body as it's being visualized, as it's being viewed by an observer sitting or standing in the ground frame of reference. An observer in the ground frame of reference is watching the motion of this rigid body. Okay, and he will say that the summation of all the moments of the forces through this point C is equal to the time derivative of its angular momentum with respect to the frame of reference from which the motion is being observed, that the ground frame of reference, and that will be equal to this expression by the property of the derivative property of this angular velocity. We can further go ahead with this. Now this is a bit tedious, which requires many multiplications, though easy but not difficult at all. So I will write this as, the expression is the derivative of hc with respect to the ground frame of reference is equal to the derivative of hc with respect to the beta frame of reference plus angular velocity of beta with respect to ground frame of reference and its cross product with hc vector. It's like this. Fine. Now let's take them one by one. Let's take this hc first. Derivative of hc in beta. Look at hc. hc is defined in beta frame of reference, and once we take its derivative with beta frame of reference, it will not be that difficult. We can write simply this as hc vector, its derivative. Be careful about it because I'm leaving some things as an exercise to the students. Derivative of this, if we assume the angular velocity of the body is constant along x-axis, along y-axis, along z-axis, okay, then it will be, sorry, we are assuming the moment of inertia and the product of inertia of the rigid body to be constant and not varying at all, okay, then it will be its derivative with respect to beta, that is the derivative of this term, derivative of equation 1 will be equal ixx. We are assuming ixx to be constant. The derivative of wx will be wx dot, and we know the derivative of angular velocity is angular acceleration. Okay, we are writing c here to denote it's with respect to c, plus the next expression, we are assuming the product of inertia to be constant as well. That will be ixy about the center of gravity, wy dot plus ixz wz dot, ixz that will be omega z dot. Okay, I cap with respect to c plus, let me rub it here, plus ixy c omega x dot plus iyy omega y dot plus about c plus I yz omega z dot about jk. Okay, and the last term will be plus ixx ixz c omega x dot plus iyz about c, omega y dot, we are taking the derivative, plus izz omega z dot, and this all is about k cap. Okay, this is the second expression of this equation. Okay, okay, this is the second expression. Let me rub this one and bring all these on one side. Okay, this is fine, we are done with this. Let me rub this one as well, this one as well. Okay, so in this equation, the equation which I am trying to solve, in this equation what we have the derivative with respect to the ground frame of reference, that's equal summation of all the moments about point C. Okay, so we are done with this we have here. Okay, now let's talk about this expression. Let's try to see what does this omega bh cross C give us. So we are done with this first part. Now let's take this part here. This part we'll do up at the top. So now let me leave this as an exercise to the students, that as far as this omega b cross hc is concerned, omega b with cross product with hc is concerned, I know that as far as omega b is concerned, omega b with respect to ground is concerned, that's equal, it's having three components, it's omega x I cap plus omega y j cap plus omega z k cap plus omega z k cap, omega z k cap. Okay, and this hc vector is here. Okay, it's here. So once I have to take angular cross product between omega b with respect to g, I have to take cross product between this vector and this vector. So it will be like this. I am giving as an exercise to the students because it will take a little bit of time for me to do it, but I will show you the procedure for doing it. Okay, so you will write I cap, j cap at a little bit of distance, and then you will write k cap. Okay, then you will write the components of omega, that is you will write omega x, then you will write omega y, and finally you will write omega z. Fine, then you will write the components of this I components of hc, you will write I components of hc, you will write then y components of hc, then you will write z components of hc, and perform the cross product the way we know how to perform the cross product. Okay, this I am leaving as an exercise to the students because I know that they can do it and it will save my little bit of time. Okay, so as soon as you take the cross product, as soon as we take the cross product, I will write everything now at the bottom. Okay, so the cross product of this term with this in this way will give me, will solve this second part of this equation for me, and you know this will come out to be equal, this should come out to be equal, as you will do it, it will come out to be equal because it will save my time. It will be equal, this expression will be equal, let me write it, this expression, the cross product here will be equal, let me write it here, this will be equal, this will come out to be equal to a big equation, it will be izz minus iyy, izz minus iyy about c, izz minus iyy, omega y into omega z, omega y into omega z, plus iyz plus iyz, omega y square minus omega z square, omega y square minus omega z square, plus omega x multiplied by omega y ixz about c, these all are about the center of gravity. Okay, minus omega z Ixy, Ixy about the center of gravity, and this entire term will be about I cap. Okay, plus the second term will be Ixx minus Iyy. Oh, sorry, Ixx minus Izzz, Ixx minus Izz, omega z into omega z into omega z into omega x, plus Ixz plus Ixz, omega z square minus omega x square, omega z square minus omega x square, plus omega y omega z Ixy minus omega x Iyz. These are all about the center of gravity. Okay, so I have forgotten somewhere to put, please take it. And the last term of this will be plus the last term plus, this is a too lengthy expression that we will get, but somehow we'll just reduce it to a very small expression. This is Iyy minus Ixx minus Ixx, that is multiplied by omega y into omega x, omega y into omega x, plus Ixy plus Ixy multiplied by omega x square minus omega y square, omega x square minus omega y square, fine, plus omega z multiplied by omega x Iyz, Iyz minus omega y Ixz, Ixz along k cap. Okay, so this expression you have to get it. Okay, once you will perform the cross product, finally you will get this expression. Now we'll solve this. We'll, sorry, not solve, we'll just reduce the expressions by giving some assumptions to it. Okay, so as far as this equation is concerned, this one is concerned, this is our second portion of this equation. Okay, and this is our HC. Fine. Now let's assume the body is symmetric. Let me rub it here, because this will make the life easier for us. Let's assume that the rigid body under investigation, rigid body is symmetric. The rigid body is symmetric about an axis system, about an axis passing through C. We assume that this rigid body, which we are analyzing, is symmetric about C. That is, this is a rigid body, this is C, and we are assuming that this is symmetric. That is, one of the axes or both the axes are the axes of symmetry. Okay, what does that mean? If we are assuming, let this to be our y-axis and this to be our x-axis, and we are saying that these axes are the axes of symmetry. Okay, that means the product of inertia about the xy or yz system, that is Ixz, Iyz, Ixy, Iyx, okay, Ixy, Iyx, Ixz, Iyz, okay, and Iyz and Iyz, Izy. All these products of inertia are equal to 0, because we know that about the axis of symmetry, the rigid body has, the rigid body has the products of inertia equal 0. That is, if our rigid body is symmetric, then all the terms, that is, this term is equal to 0. We have to rub this term. Let me clean it. We have to rub this term. We have to rub this term. We have to rub this term, this will be 0. We have to rub this term, okay? And in this expression, we have to rub this term as well. We have to rub this term as well, okay? Let me already rub these things to create a clean picture, okay? And from this expression, I have to, this will go because of the symmetry axis. Xz is 0, xy is 0, therefore these terms, this term will also go, okay? This is Ixx, Izz, this is Ixz, this is also equal to 0 for symmetric body. Ixy, Iyz, this is also equal to 0 for symmetric bodies, this will also go. Iyy, this is okay. This Ixy is 0 for symmetric bodies, this will also go, and this term will also go, okay? So I don't need this HC anymore, I will also clean it. So let's see how we have, what we have obtained now. We have obtained a very simple expression that expression we need to remember and use, okay? So we will sum up what we have obtained now. Let me rub this one. So we had HC, okay, we had HC, derivative of HC about the ground frame of reference is equal the sum of all the moments about point C of the rigid body. It is equal, first I will write the expressions for the derivative of HC. The derivative of HC is this, that is Ixx omega x, Ixx omega x dot about I cap plus Iyy omega y dot. Iyy omega y dot, and this is about j cap plus the last component is Izz omega z dot k cap. This is done, fine. So I will rub this expression as well. This we have written, so we'll clean it. Okay, this I will clean. Then the last one is this expression, the components of this expression, they are plus I zz minus Iyy multiplied by omega y into omega z along I cap. Then this expression plus Ixx minus Izz omega z into omega x along j cap, and the last component is plus Iyy minus Ixx into omega y into omega z. Okay, this expression. We can further reduce this. Let me clean the pictures. See from where to where we are going and how much it takes to get these equations simplified. Okay. So what we will obtain now, we'll get a very simplified version of this. We'll write this as MC. Directly I will write this as vector is equal to, this is equal, okay, I will put these I components under one cap, so I will write this as Ixx omega x dot plus Izz minus Iyy multiplied by omega y into omega z I cap, then the j caps together, plus I y omega y dot, that is this, with plus I xx minus I zz omega z omega x j cap, and the last one plus I zz omega z dot, the derivative of the angular velocity, plus I y minus I xx omega y into omega z multiplied by k cap. This gives us the derivative of the angular velocity vector with respect to the ground frame of reference when angular velocity is measured with respect to the center of gravity. And these equations are called the Euler's equations of motion. These are called the Euler's equations of motion. These are called Euler's equations of motion of a rigid body in 3 dimensions. Of a rigid body of a rigid body in 3D. These are called Euler's equations of motion. Now, this is the first phase of it. Now we will be using these Euler's equations of motion and to solve few problems, few questions from our mechanics, and then we will go to the impulse and momentum and work and energy. So the application of the equations of motion of Euler equations of motion is very important for us, and we need to understand them properly so as to visualize what's actually happening and how we can use these equations to understand the motion of a rigid body in 3 dimensions. That we'll be doing hopefully in the next class. So thanks very much.